What's up everybody and welcome to a new video. And in this video, we're going to go over my notes for data types in Python. So what are data types? To me, they are simply the fundamental units or building blocks to work with. And the available data types are numbers, strings, booleans, and none. And in this video, we're going to start to go over my notes for numbers. So here, the first note states that there are three different types, namely there are integers, floats, and complex numbers. So for example, if I use here the built-in function type, and if I pass it a 3, then you can see that this is an integer. And if I pass it a 3.5, then we get here a float. And then lastly, if I pass it a 3 plus 5j, then we get here a complex number. So this is what complex numbers look like. And here I also have a side note, namely complex numbers are used in some scientific applications. So for example, some of those applications are signal processing, control theory, electromagnetism, fluid dynamics, quantum mechanics, and so on. i.e. Most people probably don't really need them in their use cases. So for example, so far I've never seen them being used anywhere. Okay, so that's the side note. And with that, now we've covered this first note here. Then the next note is about the relationship between the different types of numbers. And therefore I've prepared here this illustration. So let me open that. So here, as you can see, integers are the smallest set of numbers. Then the next bigger set are floats, and they encompass integers. i.e. that means that floats can actually represent integers. So for example, if I type here 3.0, is that equal to 3? Then we get a true. And then the biggest set of numbers are complex numbers, and they encompass floats and integers, i.e. they can also represent, for example, integers. So if I type here 3 plus 0j, and then check if that is equal to 3, then we get a true. And they can also, complex numbers can also represent floats. So if I type here 3.5 plus 0j, and then check if that is equal to 3.5, then we also get a true. Okay, so this is the relationship between the different types of numbers. Then the next note is about doing calculations with the different types of numbers. Namely, in that case, the type of the result is always the most encompassing number type, i.e. whatever the bigger set of numbers is. So for example, if we do a calculation with an integer and a float, then the result is gonna be a float. So to see that, let's simply type here 5 plus 2.0 and then run this. And here you can see the result is 7.0, so the result is a float. So now let's look at an example calculation where we use an integer and a complex number. So therefore, let's simply type 5 plus 2 plus 0j. And if I run this, then you can see here the result is a complex number. And then lastly, let's do a calculation with a float and a complex number. So therefore, let's simply type here 5.0 plus 2 plus 0j. And now if we run this again, we get here a complex number. So this is what happens when you do calculations with different types of numbers. And with that, we've already covered all the main notes. So now let's go over these side notes here. And the first one is about the available attributes of numbers. And to show them, I've prepared here some code. So let me paste this here. So here we have three variables, A, B, C. A is an integer, B is a float, and C is a complex number. So now let's first look at the attributes of integers. So therefore, let's simply type here a dot, and then let me invoke here IntelliSense. And here you can see that there are 4 available attributes. So we have here an imaginary part, a denominator, a numerator, and a real part. So for example, if we look here at the numerator, then we can see that this is 2. If we look at the denominator, then we can see that this is 1. If we then look at the real part, then this is also 2. And then lastly, let's also look at the imaginary part, which is 0. in this case. So those are the available attributes for integers. So now let's look at the attributes for floats. So therefore, let's simply type here b, and then again, let's invoke IntelliSense. And then here you can see that there are only two attributes available, the imaginary part and the real part. So there are no numerator or denominator for floats. So then lastly, let's also look at complex numbers. And here again, there are only two attributes, namely the imaginary part and the real part. So again, no numerator or denominator. So again, let's just look here at the imaginary part. And here you can then see that this, in this case here for this 2 plus 5j, the imaginary part is actually then 5.0. Okay, so those are the attributes that are available for numbers in Python. Then the next side note is about available methods. And here I have prepared an illustration that shows all the methods by type of number. So let me open that here. And then here in this illustration, you can see all those available methods. And as you can see, for integers, only those first 7 here are available. For floats, those first 3 and the last 2 here are available. And for complex numbers, only this conjugate method is available. And now what I want to do is I just want to quickly demonstrate those two methods here. So let's start with the isInteger method. And therefore, I've again prepared here some variables. So let me paste those. So here we have ABC. A is 2, B is 2.0, and C is 2.5. So now let's use this isInteger method. So let's say A is integer. In that case, then we get a true. If I say B is integer, then we also get a true. And if I say C is integer, then we get here a false. So that's this isInteger method. Now let's get to this asInteger ratio method. So again, therefore I have prepared here some variables. So this time A is again 2, then B is 2.0, C is 2.5, and D is 2.3. So now let's use this asInteger ratio method. So if we say here A asInteger ratio, then we get here a 2 and a 1. If I say B asInteger ratio, then we also get a 2 and a 1 here. If I say C asInteger ratio, then we get here a 5 and a 2. And then lastly, if I say here D as integer ratio, then we get those two large numbers here. Okay, so those are the two methods that I wanted to demonstrate. Then the next side note is about special notations. And here the first one makes use of underscores. So to demonstrate that, I've prepared here again a variable, and it is this large number here. And this is somewhat difficult to read, so it's not easy to see if this is 100,000, if this is a million, or if this is 10 million. And therefore you would actually need to count the zeros. So here then you could see that there are 6 zeros. So this here is actually a million. And this can be done somewhat more easily with by using underscores. So for example, what you can do is say number equals 1 underscore 000 and then underscore 000. So this here is then also a million. And however, if I now print out this number here, then you can see internally those underscores are not used. So those underscores here are really just for the programmer, so that it is easier to read such large numbers here. And then here I also have a side note, namely underscores don't really have an effect. They could be used completely arbitrarily. So for example, what I could do is here say 10, then underscore 0, underscore 000, underscore 0. So again, here I have 6 zeros. So this gives us then again a million. Okay, so that's the first special notation. And then the second special notation is this scientific notation here. So you can make use of scientific notation. So for example, instead of writing, for example, 1000, what you can do is simply say 1 e and then 3. This also gives you 1000. Or for example, instead of saying 0.001, instead of doing that, you can also simply say then 1 e and then minus 3. This also gives you then 0.001. Okay, so those are the available special notations. So then the next side note is about floating point arithmetic. Namely, there is a certain problem with that. So for example, if I say here 0.1 plus 0.2, and then if I wanted to compare that to 0.3, then obviously you would think that this comparison here should be true, because 0.1 plus 0.2 is obviously 0.3. However, if I run this here, then you can see that we actually get a false. And this is what I mean by the problem of floating point arithmetic. And the cause for this problem is the combination here of infinite numbers with finite resources. So for example, if we take here this ratio 1/3, and if you want to translate that or transform that into a decimal number, then we would get the number 0.33333 and so on, i.e. we would get an infinitely long number. The computer, however, only has finite resources, and therefore obviously it can't represent infinitely long numbers. So then the number has to be cut off at some point, and this then in turn introduces rounding errors. And the same kind of logic applies to our problem here. Namely, the computer obviously works with binary numbers, so zeros and ones. This leads to the fact that, for example, 0.1 in base 10 is then a number that is infinitely long in binary. So if you translate a 0.1 into a binary number with zeros and ones, then you get the same effect that we had here when we transformed this ratio into a decimal number. i.e. The computer, however, therefore then doesn't work with exactly 0.1 or 0.2 or 0.3, but it works with approximations. And I can show you that by using the built-in function format. And here, if we format a 0.1 into a number with 30 decimal points, then we get this number here. And we can do the same thing for 0.2 and 3. So let's do that. So here for 0.2, the number looks like this. And for 0.3, the number looks like this. And that's the reason why we get here a false, because this number here plus this number is not exactly the same as this number here. Okay, so that is the problem and the cause, or the problem of floating point arithmetic and its cause. So now let's get to the effects. Namely, the first one is that comparisons can lead to strange behavior. So this is what we've already seen here. And what you can do to get around that is the following. So you can import the math module, and then from that module use the isClose function. And here what you can do then is to say 0.1 plus 0.2, and then check if that is close to 0.3. And now if I run this, then this time we actually get a true and not a false. Okay, so that's the first effect. And then the second one is that calculations with floats might have rounding errors. So for example, if I say here 0.1 plus 0.2, then you can see that the result of that is actually 0.30004 and not exactly 0.3. And in most cases, especially just for a single computation, this probably doesn't really matter because you don't need such a high precision anyway, i.e. the rounding errors are many places behind the decimal point. So in most cases, it's probably not going to be important if the result of this calculation here is exactly 0.3 or if it is 0.30004. However, if you do many computations, then these rounding errors here, they can then add up. So for example, if I say here n equals 0, and then for I in range 10 million, and then here in each iteration, let's add a 0.1 to this n here. So we're going to say n plus equals 0.1. And then let's also print out the n. And now what we should get here as a result is that n should be 1 million. However, as you can see, it's 999,999.9998 and so on. So we don't get an exact result here, and the rounding errors add up. So in those cases, then when you need a more exact arithmetic, then you can use the decimal module or the fractions module. And here I've prepared a code example with the decimal module. So let me just copy and paste that. And here what I'm doing is I'm importing the decimal class from this module. And then here when we initiate the n, I initiate that as an instance of that decimal class. And then here I also do the same thing when we add the 0.1 to this n. And then here, as you can see, the trade-off of doing it this way is that the calculation here takes much longer than it did when we didn't use that module. However, as you will see in a moment here, the result of this calculation is then much closer to 1 million than it is when we didn't use this module. And the same thing also happens when you use here the fractions module, for example. In that case, then you get this result here. Okay, so those are the effects of floating point arithmetic. And with that, now we've covered all the points that I wanted to cover with respect to floating point arithmetic. So now let's get to this last side note, which is this question here: why use integers when you could also just use floats? And my answer would then be that integers require less memory and or are computationally more efficient. However, this is probably negligible for most use cases because the differences are just very small. And in fact, technically integers are not really necessary. JavaScript, for example, only has floats. However, some potential use cases for integers are, for example, showing intent. So for example, when a parameter of a function is supposed to represent a whole number. So to show that, I've prepared here some example function. So let me copy that and paste it. So this function here is called add to cart, and the parameters are product ID and n items. And both are supposed to represent integers. So for example, for this n items parameter here, you could imagine that you only should be able to buy, for example, 2 apples or 3 apples, but you shouldn't be able to buy 2.5 apples. So that's why here this n items parameter is specified as an integer. So that's the first use case, showing intent, and then the second one is working with currency. Namely, in that case, you can express everything in cents to avoid the problem of floating point arithmetic that we just talked about. So for example, instead of saying here $0.1 plus $0.2, which is then $0.33004, which we've seen before, which obviously then has some rounding error. Instead of doing that, you can simply express everything in cents and say 10 cents plus 20 cents, and then you get the exact result of 30 cents. So this way then you can avoid the problem of floating point arithmetic. Okay, so with that now we've covered all the side notes, and with that we've covered all the notes that I wanted to cover with respect to numbers in Python. So then in the next video we're going to start to go over my notes for strings in Python. So thanks for watching, and hopefully I will see you in the next video.